Hey everyone, Maud Ikram here and welcome back to the channel. Today we're cracking open the digital skull and diving deep into the heart of your computer, the CPU. This little chip is basically the brain of your entire system, crunching numbers, executing instructions, and juggling tasks faster than you can say silicon wafer. We're going to break down the main components that make this little monster tick, so buckle up because things are about to get nerdy. First up, we've got the ALU, or Arithmetic Logic Unit. This is one of the most critical components of your CPU, the brain of your computer. Without the ALU, your computer wouldn't be able to perform even the simplest of tasks. This bad boy is like the pocket calculator of your CPU. But instead of just basic math, it handles all the arithmetic and logical operations. Imagine a calculator on steroids, capable of processing complex equations and logical decisions at lightning speed. We're talking addition, subtraction, multiplication, division, you name it, the ALU chews through it like nothing. Whether it's calculating the trajectory of a spaceship or simply adding up your grocery bill, the ALU is on it. But it's not just about numbers, oh no, the ALU is also a master of logic. It can handle complex logical operations that are essential for decision-making processes within the CPU. The ALU also handles logical operations like AND, OR, NOT, and XOR. These operations are the building blocks of decision-making in computing. They allow the CPU to make choices based on different conditions. These are crucial for decision-making within the CPU, like figuring out if a condition is true or false. For instance, when you're playing a video game, the ALU helps determine if your character has enough health to survive an attack. Think of it like the CPU asking itself, is this value greater than that value? Okay, then do this. It's constantly making these comparisons to execute the right instructions. The ALU is the one doing the heavy lifting, making those comparisons and spitting out the results. It's like the unsung hero of your computer, working tirelessly behind the scenes. It's the workhorse of the CPU, constantly crunching numbers and making decisions to keep your computer running smoothly. Without the ALU, your computer would be nothing more than a fancy paperweight. So next time you boot up your computer, take a moment to appreciate the incredible work of the ALU. Next, we've got the control unit, or CU, and this is where things get interesting. The control unit is essentially the brain within the brain of your computer. If the ALU is the workhorse, the CU is the conductor of the orchestra, making sure everything runs in perfect harmony. Just like a maestro ensures that every musician plays their part at the right time, the CU ensures that every component of the CPU performs its function precisely when needed. It's the CU's job to fetch instructions from memory, decode what they mean, and then orchestrate the entire process. Imagine it as a translator that speaks the language of the software and converts it into actions that the hardware can understand. Once the instructions are decoded, the CU directs the other components of the CPU to execute those instructions in the correct order. This involves a series of complex steps, each requiring precise timing and coordination. Think of it like a complex traffic system directing the flow of data between the CPU, memory, and all the peripherals connected to your computer. Just as traffic lights and signs ensure that vehicles move smoothly and safely, the CU ensures that data flows efficiently and without errors. The CU is calling the shots, making sure the right data gets to the right place at the right time. It manages the data paths, ensuring that each piece of information reaches its destination without any hiccups. Without the control unit, the CPU would just be a bunch of components sitting around twiddling their thumbs. They would have no idea what to do or when to do it. The CU brings order to chaos, transforming a collection of electronic parts into a powerful, functioning computer. In essence, the control unit is the unsung hero of the computing world. It works tirelessly behind the scenes, ensuring that every operation, no matter how small, is executed flawlessly. So the next time you marvel at the speed and efficiency of your computer, remember the conductor of this intricate orchestra, the control unit. Now let's talk about registers. These are like tiny little scratch pads built right into the CPU, used to store data that the CPU needs to access super quickly. We're talking about intermediate results of calculations, memory addresses, and even the instructions themselves. Registers are like the CPU's short-term memory, holding on to the most important information so it doesn't have to keep going back to the main memory for it. This is crucial for speed, because accessing registers is way faster than accessing the main memory, which is like the difference between grabbing something off your desk versus digging through a filing cabinet. Speaking of speed, let's talk about cache memory. Cache memory is a crucial component in modern computing, often overlooked but incredibly vital for performance. This is another type of memory, but it's even faster than the main memory and sits much closer to the CPU. Think of it as the VIP section of memory, reserved for the most important and frequently accessed data. Cache memory is like the CPU's secret stash of frequently accessed data and instructions. It's designed to speed up the data retrieval process, ensuring that the CPU can access the information it needs without any significant delays. It's like having a mini fridge right next to your couch, so you don't have to keep getting up to go to the kitchen. Imagine watching your favorite show and having all your snacks within arm's reach. That's how cache memory works for the CPU. When the CPU needs to access a piece of data, it first checks the cache. This is because accessing data from the cache is much quicker than fetching it from the main memory. If it's there, boom, instant access. This rapid access significantly boosts the overall performance of the computer, making tasks run smoother and faster. If not, the CPU has to go to the main memory, which takes longer. This delay can slow down the processing speed, especially if the data is not readily available in the cache. The bigger the cache, the more data it can store, and the faster your computer can run. A larger cache means that more frequently accessed data can be stored close to the CPU, reducing the need to access the slower main memory. Over the years, cache memory has evolved significantly. Early computers had very limited cache, but modern CPUs come with multiple levels of cache, each designed to optimize performance. Typically, there are 3 levels of cache: L1, L2, and L3. L1 is the smallest and fastest, located directly on the CPU core. L2 is larger but slightly slower, and L3 is even larger and shared among multiple cores. This multi-level cache system ensures that the CPU has quick access to the most critical data, while still being able to store a larger amount of data close by. This layered approach balances speed and capacity, enhancing overall efficiency. As technology continues to advance, we can expect even more sophisticated cache memory systems, further pushing the boundaries of what our computers can achieve. The CPU's secret stash will only get smarter and faster, making our digital experiences even more seamless. Now, how does all this data actually move around? That's where the bus interface comes in. This is like the communication highway of your computer, connecting the CPU to all the other components like memory, storage, and peripherals. The bus interface handles the transfer of data, addresses, and control signals, making sure everything is flowing smoothly. Think of it like a network of roads and highways, with data packets as cars and trucks, all moving along their designated routes. The bus interface ensures that the right data gets to the right destination at the right time, keeping everything running in sync. But what keeps everything synchronized? What sets the pace of this digital dance? That would be the clock unit. This little component generates a timing signal, a kind of heartbeat for your CPU that synchronizes all the operations happening within the chip. The faster the clock speed, measured in gigahertz, the more operations the CPU can perform per second. It's like the tempo of a song, dictating how fast or slow everything runs. Finally, we have the instruction decoder. Remember those instructions the CU was fetching? Well, they're written in machine language, which is basically just a bunch of ones and zeros. The instruction decoder acts like a translator, taking those binary instructions and converting them into a series of signals that the other CPU components can understand and execute. It's like having a real-time interpreter for a foreign language, allowing the CPU to understand and execute the instructions it receives. Without the instruction decoder, the CPU would just be staring at a bunch of gibberish. And there you have it, the main components of a CPU that work together to power your computer. From the ALU crunching numbers to the control unit directing traffic, it's a symphony of technology happening right under our fingertips. Understanding how these components work gives you a deeper appreciation for the complexity and power of modern computing. So, next time you're staring at your screen, take a moment to think about the billions of calculations happening every second within that tiny CPU, all thanks to the coordinated efforts of these amazing components. Stay tuned for more tech insights and don't forget to like and subscribe.